The title of today's webinar is Solar Resource Forecasting, and we have 3 expert panelist speakers who will share their insights and answer some of your questions. Dise's president, Dr. David Renee, will moderate the webinar. So that's all from me for the moment. I hope you enjoy the webinar, and Dave, the floor is yours.
Well, thank you very much, Joanna, and welcome everybody to our webinar. By way of introduction, I just wanted to note that the recent Paris Climate Accord provides significant global motivation for the rapid deployment of large-scale renewable energy programs. The successful commercialization of solar photovoltaic technologies will be a growing and major component of these programs. However, because solar PV is a variable energy resource, accurate solar forecasts are going to be needed to provide essential information to utilities in managing and optimizing the contribution of these resources in the grid. So in today's webinar, we're going to learn more about the current capabilities to forecast accurately the variable output of solar systems over hours ahead and days ahead time horizons. And as Joanna said, we are going to hear from 3 expert speakers who will each give us an overview of the current status of R&D and application of solar resource forecasts to assist utility operations. So with no further ado, I would like to introduce our first speaker. He is Dr. Philippe Loret of the Piedmont Laboratory of the University of La Réunion, France, located on Réunion Island in the Indian Ocean. So Philippe, I'll turn it over to you.
Thank you, Dave. This presentation related to short-term solar forecasting is based on works done with my colleagues Mathieu David and Luis Mazzola. The goal of this presentation is to assess if the combination of different types of data, say for instance ground data or satellite data, or combination of models, can increase the forecast accuracy when compared to a single model forecast. Due to the intermittent character of the solar energy, accurate solar forecasts at different time steps are needed in order to increase the penetration of solar energy into electricity grids. This figure illustrates the different forecasting methods for different spatial and temporal scales. Depending on the forecast horizon, different input data and forecast models are appropriate. For instance, time series model with local irradiance measurements as inputs are used to provide point forecast up to a few hours ahead with a temporal resolution from minutes to 1 hour. Forecast based on cloud motion vectors, based on satellite images are produced for forecasting horizon up to several hours ahead, typically 4 to 5 hours ahead. For very short-term forecasting horizon, one can use also cloud motion vectors based on sky images. And finally, for forecast horizon from 6 hours onwards, forecast based on numerical weather prediction models and WP models are generally more accurate. Each forecasting horizon is also related to specific need of the grid operator. For instance, day-ahead forecast with NWP model may be beneficial for unit commitment or day-ahead markets. And also, short-term forecasts are needed for operational planning and also, among others, for adaptation of the day-ahead schedule. In this presentation, we will focus on intraday solar forecasting, that is, for forecasting horizon from 1 hour to 6 hours, with a time resolution of 1 hour. The forecasting model will be based on linear time series model. or machine learning techniques like artificial neural network. For PV power applications, GHI, or the global solar horizontal irradiance, is the variable of interest, as PV power output is directly related to the level of received global solar irradiance. Thus, forecasting GHI is a key feature of the PV power prediction. The basics of a forecasting statistical model consists in taking past ground measurement of GHI to provide point GHI forecast up to a few hours ahead. As no forecast is perfect, there will be, of course, an error between reality and the prediction. In addition, the forecasting error may increase with increasing forecast horizon. The question that may arise are, can we make use of information provided by NWP model? Can we combine, for instance, direct GHI forecast provided by numerical weather prediction model like ECMWF to increase the accuracy of the intraday solar forecast? We can make even a step further by combining ground plus NWP plus satellite data. And for instance, we can ask the following question: can the spatial temporal information brought by gridded satellite-derived GHI be beneficial for improving the forecasting accuracy? The answers at this question are yes, at least with the result presented here. To illustrate our discussion and build the forecasting models, we use GHI data from two sites of the Surfride network in the continental US, Desert Rock in Nevada, which experiences an arid climate, and Fort Peck with a continental climate. Also, we work with three insular sites, two sites from La Réunion Island, located near Madagascar in the Indian Ocean, Saint-Pierre and Le Tampon, and one in Gran Canaria Island, Las Palmas, in the north of the island. Islands usually possess a complex orography, which causes the formation of local clouds that makes solar forecasting a challenging task. I mentioned before that the variable of interest is the GHI. Actually, we don't work directly with the GHI time series. GHI time series has two components: a deterministic part, which is completely predictable and can be modeled by clear sky model. This part is due to the course of the sun in the sky, daily and early course of the sun. And the second part is a stochastic part due to the passing of the clouds in the sky. This second part is captured by the clear sky index, which is the ratio of the measured GHI to the theoretical GHI observed under clear sky conditions. Hence, the forecasting models are fitted to the clear sky index time series. The value of the clear sky index are comprised theoretically between 0 and 1, and this value depicts different sky conditions. For instance, values of clear sky above 0.8 correspond to clear sky, and while values below 0.3 correspond to overcast sky conditions. This slide represents the distribution of the clear sky index for the four sites. I think the site of Desert Rock in Nevada experiences high occurrences of clear sky. It is completely normal. In addition, this site exhibits a low solar variability. Conversely, at the opposite, the insular site from La Réunion, Le Tampon, has more occurrences of intermediate and variable sky conditions. This prior site analysis is very important as the sky condition experienced by a particular site will have an impact on the forecasting performance of the different methods, and we will see that after. For the benchmarking of the different forecasting models, we will evaluate two reference models, the simple naive model core persistence and a climatological mean model. We also build a linear time series model, a recursive ARMA, that means with a recursive estimation of the parameters of the model, and also a machine learning technique, artificial neural network. To assess the accuracy, that is the forecasting error of the different techniques, we will make use of the root mean square error, which is a common metric used in the solar forecasting community. We also propose a second metric that characterizes the focus scale of each model. Yeah, indeed, it is useless to build complex forecasting models if the latter cannot beat a simple model like the persistence model. With this definition of the focus scale parameter, the persistence model has a focus scale of 0%, and a value of 100% denotes a perfect focus. Further, the higher the S-scale score is, the better the improvement is. This slide shows the forecasting performance of the two reference models. Persistence is the simplest model that assumes that the clear sky index for each forecast time horizon H depends only on the previous measured value of the clear sky index. While the climatologic mean model, this is a model which is independent of the forecasting time horizon. It produces a constant forecast of the clear sky index that corresponds to its mean historical value. And as shown by the figure, the performance of the models degrades with increasing forecasting horizon. Sorry. As I mentioned before, the performances of different models depend heavily on the sky condition experienced by each site. Indeed, we have a forecasting error of 15% for 1 hour ahead for Desert Rock and 30% for Le Tampon in La Réunion Island. The persistence scores are very representative of the variability in the time series and to a certain extent of the forecast difficulty at a particular site. Let us recall that Desert Rock experiences high occurrences of stable clear days, while Le Tampon exhibits more variable and cloudy sky conditions. In this slide, we recall the principles of the forecasting model with past on-site measurement of clear sky indices as input. The model predicts the clear sky index time series for each forecasting hour age of interest, and once the future clear sky index has been forecasted, the corresponding JHI is calculated by applying the clear sky model backward. This slide shows the performance of the statistical models with only ground data as inputs. As seen, the neural network and the linear ARMA model perform better than the reference model for forecasting time horizon greater than 1 hour. Further, compared to the persistence model, the gain in RNSE increases with the forecasting horizon. Finally, one interesting thing to note in this slide is that a simple linear model like the recursive ARMA performs equally well or slightly better, depending on the site, than a nonlinear model such as the neural network. Now we make a step further by incorporating additional inputs provided by a numerical weather prediction model like the IFS, Integrated Forecast System model provided by the European Center for Medium Range Weather Forecast, ECMWF. This picture shows the ECMWF grid and the characteristic of its implementation for La Réunion Island. Let us recall that the goal here is to use the day-ahead JHI forecast provided by the ECMWF in order to improve the forecasting performance of the intraday solar forecasting. Actually, we took as additional inputs of the neural network two quantities that are predicted by ECMWF, namely the predicted clear sky index for time horizon H and also the total cloud cover. And this figure clearly demonstrates the improvement at each forecast time horizon of the forecasting accuracy obtained from the combination of day-ahead ECMWF forecast with on-site measured irradiance. We can see better this improvement by plotting the forecast skill of the method. Let us recall that the persistent model has, by definition, a skill score of 0%. And one can see that higher values of S-skill scores are obtained with the combination of on-site measured irradiance, ground, plus data coming from ECMWF. The next step consists in using satellite gridded data. We will illustrate this on the site of Las Palmas in the island of Gran Canaria. The idea here is to use satellite-based surface solar irradiance estimated from the satellite images in order to improve a local JHI forecast. In this application, we use satellite-derived JHI obtained from the EUCLIM database. These satellite images present a huge amount of input data that we need to select carefully. And for this application, the selection of the satellite-derived JHI estimates as additional inputs of the neural network was done by calculating the cross-correlation between the ground clear sky index and satellite clear sky indices for 4 time lags. And a pixel was selected if its correlation was greater than 0.5. This slide shows the forecasting skill of the 3 possible configurations. Overall, I think the forecast skill of the combination of ground measurement plus ECMWF data and satellite data is better than the other two. It appears that this last model realizes the best trade-off compared to the other two. And further, it seems that the weight of satellite data is more important at time horizon lower than 3 hours, while the weight of NWP data becomes more important at horizon greater than 4 hours. As a conclusion, we can state that there is a high potential for improving forecast accuracy by combining different type of data, different type of models, with, for instance, the help of statistical learning approaches like neural network. Future work will be devoted to the evaluation of other input parameters provided by ECMWF, for instance. Cloud direction may be beneficial for the selection of the satellite pixel in the upstream direction of the flow field. Also, as a simple linear recursive ARMA model did quite well against neural network, we plan to implement a version of this linear model that will integrate exogenous inputs. To conclude, I will, if one is interested in the use of exogenous inputs in forecasting models, I will suggest these papers. Thank you for your attention.
Well, thank you very much, Philippe, for that very interesting presentation. And now I would like to first remind everybody, we have a number of people that are attending this webinar. If you have any questions for any of the speakers, please use the questions feature on the webinar software on your computer to ask your questions. What we will do is go through all three of the talks first, and then as much time as we have, we will use to, I will ask the, or repeat the questions to the speakers for the remainder of the webinar. After the webinar is completed, we will arrange to have all the questions answered by the speakers, and those answers will be online. Okay, next we will have Dr. Elke Lorenz of the Energy Meteorology Group, Institute of Physics at the University of Oldenburg in Germany. Okay.
Yeah, thank you for the introduction. So I will present on local and regional PV photovoltaic power forecasting based on PV measurements, satellite data, and numerical weather predictions.
Sorry,
yeah, and the work I will present.
I'm just going to jump in there. Philippe, could you turn your webcam off? We're all seeing your webcam at the moment. And Elke, could you, you see that little red button, the arrow on your GoToWebinar control panel? Could you click that to minimize your control panel? On the very top, there's a little red, no, not that one, the red arrow. Yes, that one, if you just, sorry to interrupt.
Okay, no problem. Okay, so again, I will present on local and regional PV power forecasting based on photovoltaic measurements, satellite data, and numerical weather predictions. And the work I will present has been prepared in cooperation with my colleagues from the Energy Meteorology Group in the University of Oldenburg. First, I want to give a short outline of my talk. And I have technical problems, sorry. Okay, here's the outline. I want to start with some background information on grid integration of photovoltaic power in Germany and the resulting forecast requirements. Then I want to give you an overview on our PV power prediction system. And in the last part of my talk, I will give you an evaluation of different data and models for different forecast horizons and the benefit of combining different models. Yeah, first for the background, grid integration of photovoltaic power in Germany. In Germany, at the end of 2015, we had 39.5 gigawatt peak installed power. And this means that up to 50% of the overall electricity demand in Germany can be covered by PV. So for illustration, I have a graph of load and contribution of renewable energies for some days in summer. So we can see the typical load curves with high load during noon and less load during the nights. And we can also see the share of PV contributing to this load. And we can see that on some days we have really high contribution, up to 50%. But there's also other days, the last day in this time series, where there's only small contribution of PV power. And because of this strong variability of solar power, it's necessary to have forecasts to adjust and balance these variabilities. This grid integration of PV power in Germany is done by marketing PV power at the European Energy Exchange. So a large part of this marketing is done by the transmission system operators, and they have to market their share of the overall feed-in of all PV systems in Germany, so they need regional forecast of the overall feed-in of PV power rather than single-site forecasts. But there's also the option of direct marketing, which is currently increasingly used, for example, by plant operators, and they market the PV power of single plants or several plants together, and they will need local forecast for the sites of their plants. So the forecast horizons necessary are determined by the organization of the European Energy Exchange. So the process starts on the so-called day-ahead market, where energy contingents for the next days are traded with hourly resolution, and for this we need day-ahead forecasts of the PV power. Next step is the intraday market. There is the option of additional trading to adjust on the basis of intraday forecasts, which is generally more accurate than day-ahead forecasts. And this intraday trading is possible up to 45 minutes before the delivery of the energy contingents. And finally, to adjust between remaining deviations between feed-in and demand, there is balancing power, which can be used to adjust for these deviations. So forecast accuracy is very important for the complete chain of marketing. So forecast errors of the day-ahead forecasts can cause high prices on the intraday market. If there is not enough, or the prediction is too low, there will be a lot of purchase on the intraday market, so there will be high prices. And the forecast errors of the intraday forecasts determine the need of balancing power, and balancing power is generally much more expensive than the regular trading. So summarizing, accurate PV power forecasts are very important for cost-efficient and reliable system integration of solar power, as we have seen here for the example of marketing of PV power in Germany. In the next slide, I want to give you an overview on our forecasting scheme. So we use the same data sources as we have already seen in the presentation before. For the very short-term horizons, it's very important to have a good knowledge of the current state. And the best knowledge on the current state we can get from measurements. So in our case, we use PV power measurements as the first element of our forecast. If we want to describe the future situation, it's not enough to know the current situation, but to model the change in the cloud situations. And this can be done by seeing clouds coming to a certain location from satellite images. And this cloud advection approach is applicable for forecast horizons of several hours ahead. And for forecasts of several days ahead, or more than several hours ahead, we need numerical weather prediction models that can describe the full dynamics of the atmosphere, not only advection of cloud, but also convection of cloud formation and dissolution of clouds. So this is the input data we use for our forecast, and in a next step, to derive the PV power predictions, we apply PV simulation and statistical models. In the next slides, I want to give you some more details on these different elements of our forecasting algorithm. I will start with the numerical weather predictions. We use numerical weather prediction of two models: global model forecasts of the European Center of Medium Range Weather Forecasts, and additionally forecasts of the regional model of the German Meteorological Service, DWD. And we apply a post-processing to these forecasts, a bias correction, and a combination of the two models with linear regression. So far for the numerical weather prediction. Next is satellite-based irradiance predictions. We use images from Meteosat second generation satellite from the high resolution visible range. And in a first step, we derive information on clouds from the satellite images with the Heliosat method. And yeah, we can get images with a resolution in Germany of approximately 1 times 2 kilometers, and we can get 1 image every 15 minutes. In the next step, we derive information on the motion of clouds by identifying cloud motion vectors from consecutive images, and this is done by identifying matching structures in the images. And to forecast the future cloud situation, the derived motion vectors are then applied to the current cloud situation, and the motion and the clouds are extrapolated to the future. And in a last step, we derive irradiance map from the forecasted cloud information. So last input data source is measurement data. In the presentation here, I use measurement data of more than 900 PV systems in Germany. The database includes March to November 2013, 15-minute values, and for all the PV systems where we had the data, we had also information on tilt and orientation of the system, which was used to do the PV simulation. So this was the input data sources and models. In a next step, I want to show you how we derive the PV power forecasts from these input data sources. Starting with the measurement, we apply the approach of persistence, which has already been introduced in the previous presentation. So persistence means we assume that the situation stays as it is. And to model the daily course of irradiance with this approach of persistence, we assume a constant cloud situation and model the daily course with a clear sky model. So constant cloud situation here is determined by assuming a constant ratio of measured PV power to PV power, which would be expected for clear sky conditions. To derive PV power forecasts from the other two forecast models, we apply a PV simulation tool. The forecast approaches give global horizontal irradiance. And the first step for deriving PV power from this is conversion of the irradiance to the array plane with a tilt conversion model. And in the next step, we derive the PV power output with a parametric model for maximum power point efficiency. And in a final step, we apply post-processing to better adapt the forecasts to measurements. So far the overview on the different elements of our forecasting method. In the next slide, I want to give you an evaluation. And here I will look at forecast horizons for 15 minutes to 5 hours ahead, which allows to compare the different models, and which is also the forecast horizons which are most important for the intraday market. So to evaluate the forecast, I want to start showing you some scatter plots of predicted over measured power. For the regional forecast, this means graphs are shown here apply for the average German forecast for the German average. So we can see here in both graphs in blue the scatter of the forecast of the numerical weather prediction model. In red we can see the scatter of the persistence forecast, and in green we can see the scatter of the cloud motion vector forecast. Here in this slide we have a prediction horizon of 15 minutes ahead, so we can see for this 15 minutes ahead both persistence and also cloud motion vectors are much more accurate than the numerical weather prediction models. In the next slides I will show you the same graph for increasing forecast horizon. And so the numerical weather prediction model is updated every 6 hours only, so there will be no updates. The numerical weather prediction will stay the same, but the performance of the other two models will change. So this is 15 minutes. The next slide shows you increasing scatter of persistence and cloud motion vectors for 1 hour ahead. Next step will be 2 hours ahead, so we can see here similar performance of persistence and numerical weather predictions, and still a better performance of cloud motion vector forecasts than the numerical weather prediction, further increasing forecast horizon 3 hours. and finally 4 hours. So this gives you a visual impression of the performance of the forecast algorithms. In the next slide, I want to put this in numbers. We see again the RMSE as a measure of forecast accuracy that we have seen before. And for evaluating the PV power forecasts, here we have normalized the RMSE values to the installed power, which is the current practice for the transmission system operators, which are the users of our forecasts. So in this graph, we can see again the RMSE over the forecast horizon. So for numerical weather prediction, there is no change because there is no update in this 5 hours. And we can see the increasing error of the cloud motion vector forecast with the forecast horizons. And we can see that up to 4 hours ahead, the cloud motion vector forecasts are better than the forecasts from the numerical weather prediction models. Next reference is a comparison with the persistence model. So we can see for the very short-term horizons, up to 2 hours ahead, we have best performance with this measurement-based approach, but forecast errors are increasing fast with the forecast horizon. So this is forecast errors for the German average. In the next slide, I'm comparing this to forecast accuracy for single sites. So we can see now RMSE values are on a different scale, not between 1 and 6%, but between 1 and 20% RMSE values. And we can see that the RMSE values for the German average are much smaller than RMSE values of forecast errors for single sites. Yeah, to shortly illustrate this, we can see here 2 days for German average forecast and single site forecasts for variable cloudy days. Yeah, and we can see that for the single sites we have much larger fluctuations, which are quite difficult to predict, while for the German average forecast we have very smooth curve. Yeah, and due to spatial averaging effects, it's easier to predict these average values than the single sites with the very high fluctuations. So for quantitative evaluation, we go back to our RMSE plots. And yeah, if we compare the RMSE values for single site and for the German average for the numerical weather prediction forecasts, we can see that the RMSE for the German average is about 1/3 of the single site error. So this holds for the numerical weather prediction, but it's different for the cloud motion vectors and the persistence approach. And to illustrate this, I show here again the German average RMSE plot on a different scale. And we can see here that the improvement over the numerical weather prediction is much larger with persistence, and cloud motion vector is much larger for the regional forecasts than for the single site forecast. So summarizing, we have seen that different models are suitable in dependence of the forecast horizon, but we have seen also that the spatial scale plays an important role to select the best model for a given forecast horizon. So coming back to the scheme of the different elements of our algorithm, we have seen now the evaluation for single model forecasts, and we have already seen in the previous presentation that it's beneficial to combine these different approaches. So this will be the last part of my presentation, the combination of the different input data. So yeah, to illustrate the benefit of the different models, I have chosen here a simple approach with linear regression. The combined forecast is obtained as weighted average of the single model forecast, and this coefficients or weights are fitted to measure data independent of the forecast horizon and the hour of the day in order to model the advantage or to include the advantages of different models for this different horizon. Training data is done with daily updates with the measurement of the last 30 days. And for single site forecast, we have trained for each PV system separately, and for regional forecast, we have directly trained with the average of site. This slide shows you now the weights or regression coefficients independence of the forecast horizon. In the right plot we see the coefficients, in the left plot we see again the RMSE values, and we can see that in the first 2 hours the persistence, displayed in orange here, is weighted very strongly compared to the other approaches, but the weight of persistence is decreasing fast with the forecast horizon as the RMSE is increasing, and the weight of cloud motion forecasts and numerical weather prediction is increasing with the time. So what's the benefit of this combined approach? We can see here in gray the combined forecasts, and we can see that the combined forecast outperforms the single model for all forecast horizons, and the improvement is particularly large for more than 1 hour ahead. So if we look again at the single sites, we have here a comparison of the weights or the coefficient independence of the forecast horizon for the German average on the left side and for the single sites on the right. And we can see that the weights are quite different for single sites and for the German average. In particular, we can, for example, see that the cloud motion vector forecast from satellites is weighted very strongly between half an hour and 3 hours ahead, which is not the case for the German average forecast. So it's important to do the training different for average values and for single sites. So overall results, RMSE independence of the forecast horizon for the German average and the single sites. So for both, we can see the improvement with the combined approach, and we can see again the effect that the improvement is larger for the regional forecasts. Yeah, so summarizing this part of the talk, we can see that it's what we have already seen in the previous talk, that there is a considerable improvement by combining different models with statistical learning. Summary, I want to emphasize that PV power prediction contributes to successful grid integration of almost 40 gigawatt peaks PV power in Germany. We have seen that PV power forecasts based on satellite data are better than standard numerical weather prediction forecasts up to 4 hours ahead, and we have also seen that there is a significant improvement by combining different forecast models with PV power measurements, in particular for the regional forecasts. So, thank you for your attention.
Thank you very much, Elke, for your excellent presentation. And again, just to remind everybody to please type in your questions in the question panel, and we'll try to get to as many of them as we can after our final speaker is finished. And also we will post responses to the questions online in the next day or two. Our last speaker today will be Skip Dise. He is a product manager for Solar Anywhere, which is the satellite-based solar resource assessment program developed by Dr. Richard Perez at the State University of New York in Albany. Skip is at Clean Power Research, a company located near Seattle, Washington, in the United States. And he will discuss some of the commercial applications of solar resource forecasts. So, Skip, I will turn it over to you.
Great, thank you very much, Dave, for the introduction. I will begin sharing my slides here. Great. So, yeah, thank you, Dave, and also thank you to the other researchers on this webinar for their great presentations on solar forecasting. Today, I'm going to present much of our work in creating an operational solar forecasting software that is used for PV fleet simulation at utilities and balancing areas. The bulk of this work has been led and really driven by Dr. Richard Perez from SUNY Albany. At Clean Power Research, we work closely with Dr. Perez and his lab to make his latest and most accurate approaches available through our commercial software tools. There are other members of his group and others at Clean Power Research who are ultimately responsible for much of what I'm presenting today. So I'd like to acknowledge them up front. Quick discussion of what I'll be talking about here, and my goal is really to share information about the following 3 topics. First, our historical and forecast software platform that is used for serving irradiance and weather data to customers, and also through our PV fleet simulation tool. Some research results that Dr. Perez has produced about a North American blended forecast that builds upon different forecast models. And finally, that application of weather and irradiance forecasting to the electric grid, and specifically talking about net load prediction for a balancing area and incorporation into a load model, not necessarily an explicit solar forecast or PV model that uses neural network learning, but a load prediction model that uses that type of approach. So, as I mentioned, we are generating Dr. Perez's latest models through a software tool called Solar Anywhere. This is a web-based platform and has traditionally served data in the United States continental and Hawaii. We've added coverage for Mexico and Canada recently, but our main feature of the tool that really benefits this work is our ability to span the 3 time horizons that are listed here. Historical climatology through real-time or nowcast, and then forecast with a rolling time horizon of 1998 through 6 days ahead. The historical model uses Dr. Perez's satellite to solar irradiance model to predict cloud cover from the satellite image pixel brightness. Recent improvements in this model and applied through historical and real-time data sets include the use of infrared satellite channels for differentiation of snow cover on the ground and cloud cover. Originally, we designed a forecast model to use 2 separate inputs targeting an hour ahead and a day ahead time frame. For the hour ahead time frame, we constructed the cloud motion vector model that's very similar to what many have presented already. It processes satellite cloud images for the prediction of overall cloud cover in the near term. In this approach, we're calculating cloud speed from consecutive images, then optimizing the cloud vectors based on a minimizing difference approach between adjacent cells. Cloud speed is then applied to a future image, and really it's a collection of gridded cloud cover indices. At the very highest resolution, we can begin to look at the variability on a very short time scale. So we can produce short minute-by-minute prediction, and we can do this for the time into the future, in the day and the hours ahead, as well as applied to our historical satellite images to generate a historic variability data set. Still staying with our original build, in the day ahead, we then brought in numerical weather prediction from what's available in the U.S., which is the National Digital Forecast Database and its cloud cover model. After years of operating this platform commercially, we learned a few areas, specifically in the North American climate, where forecast irradiance could be improved. First, we added the ability to generate a cloud motion vector for the prediction of morning hours. So in many cases, when the cloud motion vector is run on a visible image, it doesn't generate at early morning hours when the sun has not come up yet. So we added the ability to detect cloud pre-sunrise using those IR channels from the same satellite platform. Additionally, a number of global and continental scale numerical weather prediction models were added in to our blend, which allowed us to take feedback from those individual accuracy of those models and produce a mix of prediction. We optimized that mix by looking at the validation across 4 ground station sites in the continental US, and looking at a traditional metric of root mean square error or relative root mean square error here. We first plot our 2 endpoints of accuracy. What has been discussed a lot today, the persistence approach. Here we call it the smart persistence. In the hours ahead or in the current day, we're persisting the cloud fraction, and then any day ahead, so any time horizon 24 plus, we start to use a long-term climatology for that persistence model. Additionally, the accuracy of the historical satellite model in the dotted black line gives a baseline for what our skill is in generating or translating satellite images into irradiance prediction. Then we can start to add in the different forecasting models as individually as described: cloud motion, NDFD, NAM, RAP, HER, GFS, ECM, WF, and then specific mention for WRF model, which actually was not reflected here, but evaluated at the continental level and omitted due to its similarity to the NDFD results. So then, for the sake of comparison, we're highlighting the original forecast model here as the combination of the cloud motion and NDFD models. But the new model, however, takes and optimizes those prediction across all these inputs and produces a sum that is effectively greater than its parts. Similarly, when adding short-term persistence from ground, we see that accuracy improvement less than 1 hour. So that was a way that we looked at the forecast skill in development of the new model. However, that approach wasn't necessarily as applicable to utilities who are more concerned about the forecast's ability to be consistently accurate with a limited number of missed forecasts. So what's considered a missed forecast? So this type of accuracy presentation was developed by T.J. Vargas from SMUD, where he looked at the periods where the forecast was accurate in its ability to hit cloudy and clear periods, and considered the forecast to miss when it predicted cloudy forecasts in clear conditions and clear forecasts in cloudy conditions. Looking at the forecast this way and this type of error to the utility is important because they must begin to rely on the solar forecast to help them balance their grid and the supply and demand on that grid. So the orange bars that you're seeing here are ranges of a clear sky index, but within that range there was developed a certain tolerance of missing the prediction of either cloud conditions or clear conditions. So the utility was indicating that is the type of metric that they wanted to optimize for. So we can then look at the individual models again by this metric, specifically here at a single site This is the Penn State surf rad station. So combining this hit-miss metric at the 4 ground stations, we see that there's the ability of the new blended forecast to reduce the operational inefficiency to the utility as well. So with all this this work now on irradiance forecasting accuracy and developing that technique, at Clean Power Research we wanted to take what Dr. Perez has developed here and further understand what this ability could be and how it could best be applied to utilities and transmission operators that were looking to integrate solar onto their grid. Since forecasts are being generated across these large geographic areas, here we represent the state of New York. However, we talked about coverage in the US and Canada and Mexico. The application could be not only the central PV plants, but also the prediction of the total behind the meter or distributed PV generation. Taking this hit-miss metric and looking at how well it performs for a single site, so the overall new forecast, operational forecast model for a single location as opposed to a regional transmission area, which is highlighted in the yellow box here in the state of New York. And so we see a vast improvement in the ability of the gridded forecast over a larger area to give operational reliability to the transmission operator. So to further describe this concept, by combining our forecast model across a large geographic area, say the state of New York, we can begin to forecast the total PV generation on the grid, both at the distribution and transmission scales. The application for these predictions are reliant on the utility's need, and as indicated, the ability to generate historical irradiance data could be used to model scenarios of what if. So what if the amount of PV grows to reach this penetration level, this capacity? And the forecast irradiance can then be used to drive operational requirements for grid balancing in a real-time setting. So now I'm going to turn my focus to the state of California, which has the highest capacity of installed PV in the U.S. That capacity is broken up between the central utility scale or transmission tied operating plants, which have a high capacity, have a high number of panels co-located, and are lower in number, so in the hundreds of PV plants across the state. And compare that to the distributed PV, which are very high in the number of sites, as you can see on the map on the right, but have a low capacity per site rating. So then when we're focusing here on the distributed PV and generating the fleet prediction, how do we actually do that, and how do we build our PV fleet from the number of sites across the state and combining that with the irradiance forecasts? So we're starting with a database of information about the installed distributed PV capacity. Here represented 3 sites, location, modules, inverters, layout. And then we aggregate the prediction to zones specified by the transmission operator across the state. So there are 5 zones represented here, and aggregates of the distributed PV capacity are generated by this approach. So why is this important? As was presented in Germany, where the capacity is much higher, PV has the ability to affect the transmission operators' prediction of load on their system. This is a curve that was provided courtesy of the California Independent System Operator, or CAL-ISO. And what they're showing here is that the actual load on the system is changing and flattening in midday. And that progression has occurred as the capacity of PV has grown over time. The models that are used to forecast load, however, use a neural network approach, learning from measured feedback and training to explicit variables such as temperature. And as many of you will know about those types of models, or the model of PV, however, temperature is really a second order effect for PV production. So there isn't a strong correlation in those existing load prediction models to adapt to the contribution of behind the meter or distributed PV. So in this work, we've now introduced the forecast of the distributed PV into the load neural network model. The first step that we took in that work was to train the load model. This was used a historical simulation of PV capacity that changes dynamically as more systems are installed. So what you see is the simulated power from the PV systems installed. This is a region in Northern California used here for representation. That the simulated power is the light green, and the orange curve shows the dynamic capacity changes that are occurring. So as more distributed PV is installed, we want to reflect that as the conditions that the grid would have seen at the time of growth in capacity. This highlights the importance of our seamless platform, where we can pull out of it this historical information, historical irradiance data, to drive these predictions, again, of the what-if scenario. What if you have this amount of PV growing as installed capacity on the grid? So first, with the historical load training, we wanted to make sure that the input of the explicit variable of PV power actually contributed to an improvement of the historical reanalysis of load prediction. The metric that we developed in working with Itron is the operator of the load forecast model, was this so-called BTM coefficient, where a value of -1 would indicate that the exact capacity of behind the meter PV predicted matched the amount of load shed by the load forecast. So results are indicate that, and possibly this is expected to some degree, that the importance of that PV prediction grows as you near the noon time hour and into the afternoon. We then incorporated the forecast model and delivery of real-time behind-the-meter fleet forecasts, dynamically driven, for incorporation to the load training. The day-ahead results here are presented in some summary. We see that there's much improvement in the load for certain times of the day, again focusing on times when the behind-the-meter generation is contributing to the amount of offset to the gross load on the grid. And lastly, I'll mention here that we looked at the real-time pre-dispatch and ancillary services market time horizons. That's the 15 and, well, sub 15 now, but 15 was tested out through 6 hours. And the results presented here are represented as a percentage of forecasts improved. So the column on the right there is what percentage of the forecasts generated over this multi-month period were actually improved at that time horizon by leveraging the explicit PV power variable for behind-the-meter PV. And this result seems to be consistent with others have presented when talking about the incorporation of PV forecasts or radiance forecasts combined with the neural network or machine learning approach. And that in the very short term, these neural network or persistence models can quickly learn from the real-time feedback on the system. But at the near to medium term of prediction, that's the 2 to 6 hour, we see the value of that forecast, the PV forecast, growing. So that is what I have here to present. A quick recap of what we talked about. We see that the radiance forecasts can certainly be optimized for the North American climate as they can by learning from ground measurements and other reference points in training models. Application to grid operation is very much a growing need and will continue to grow as the amount of PV, not only centralized generators, but distributed PV grows. And finally, or second to last, the historical training we found to be very vital, which highlights the importance of this seamless platform going from historical, real-time, and all through forecast. And then we see some preliminary results that indicate that incorporation of these PV fleet forecasts can improve the load forecast for day ahead and then also in that 2 to 6 hour ahead time horizon. So thank you very much. I want to acknowledge Itron and specifically Frank Monforte from Itron and his work with us, and then funding from the U.S. DOE.
Okay, Skip.
Well, Joanna, back over to you.
Yeah, well, thanks. Great, Skip. Good talk. All three of these presentations were really very interesting. We've had a lot of questions come in, and we still have many people online. We have about 20 minutes to go through the questions. What I propose to do here is just take them more or less in the order they have come in. I don't know if I'll get to all of them, but I'll probably try to get to as many as I can in the next 20 minutes or so. So, and if you still want to ask questions, please feel free to do so using your question tool on the panel on your computer. Okay, so the first one came in during Philippe's talk. Since numerical weather prediction models have a particular value of global horizontal irradiance, are there any techniques for interpolating those values to a specific location, since the actual value of irradiance is different in 2 different points in a grid? So Philippe, could you take on that question?
Okay, Dave. If I well understand, it's about the numerical weather prediction forecast about GHI. That was the question, Dave?
Yeah, it's based on the numerical weather prediction models providing GHI output, but you know, they're over a very large area. So the question is whether you can interpret the output of the numerical weather prediction model to a specific location.
Actually, for Alarion Idon, when I speak about the implementation of ECMWF model, which is a numerical weather prediction model, the spatial resolution it's about for Alarion with the new version, it's about 14 kilometer. It's a square of 14 kilometer per 14 kilometer. So, of course, for island like Rayon, the resolution, the spatial resolution is very coarse, but anyway, we can use the information provided by ECMWF to increase the forecasting accuracy, even if the resolution is coarse.
Okay, good. Thank you. That's a good answer. Next question came in during Elke's talk. The questioner points out that the simulations and forecasting have been done for the U.S. and for Germany and also the Canary Islands. And the question is, have you, and I presume many of you can answer this question, but start with Elke, have you done any forecasting modeling for Latin American countries? So Elke, start with you.
Just remember to unmute your microphone, please.
So I haven't done forecasting for Latin America yet, but we had a guest student from Brazil here some time ago, and he has evaluated the ECMWF model forecasts that we are also using here for Brazil, and he got quite good results with these for Brazil too. Yeah, but in general, I think in the tropics, forecasting is much more challenging than in Europe or the US.
Okay, Philippe, do you have anything to add there, or Skip? I'll start with Philippe and then Skip.
Regarding this previous question, no, for Latin America, no. I work with mostly island, like Reunion Island. I work also with my colleagues of Gran Canaria, as you see, also with colleagues from Guadeloupe and Corsica. So mostly for insular site. And as Elke said, it is very in island, solar forecasting is a very challenging task due to the complex topography that cause formation of local clouds.
Okay, yes. And Skip, did you have anything to add there?
Sure. So from my slides, you had seen that we've started to expand the satellite coverage down, and the satellite network in Latin America is the same one that is used for North America. On the forecasting side, there are a number of challenges, including the frequency of satellite image capture, so that limit the ability to refresh the frequency of the forecast. But we have done, and looking at the timeline, as the climatology in certain areas of Latin America, expanding down from Mexico and the Caribbean as well, though not fully operational in the software product yet.
Okay, and the next question that came in, it came in during Elke's talk, but I think we perhaps have already answered it, but again, it was a question, is the operational system in Germany, and I presume the other systems that we talked about, can they be implemented in a country such as Mexico? But I believe you've all already addressed that, unless somebody has something additional they want to add. Otherwise, I'll move to the next question. Okay,
yeah, so
so
I think
the next question.
In principle, it's possible to do so, but as we have seen in all the three of the presentations, it's important to have measurement data, or it's beneficial also to have good measurement data to train optimized forecasts, to train an optimized forecast. So yeah, numerical weather predictions and satellite data are available too, but it's also good to, or it's also important to have good measurement sites, either irradiance or directly PV power.
Yes, and probably some special studies to adapt the tools to specific regions as well.
Yes, I agree.
Okay, thank you, Elke. Next question Is there a minimum number of years of past data that should be used to increase the accuracy of the solar resource forecasting? And I think, Elke, we'll start with you on that one. I think that was during your talk.
So we are using usually only a very short history to training our models. So I think we can start quite from, if we have some days or months of data, we can just start with the forecast. I mean, the basics of the model is a physical model. We have the numerical weather prediction and we have the satellite-based predictions, and the measurements are just used for model training. And yeah, so therefore it's possible to start without long history of measurements. Does this answer the question?
Yes. Does anybody else, Philippe or Skip, do you want to have anything to add to that?
Usually, when we train our statistical model like neural networks, usually we use 1 year of training data. But as I said in the presentation, we work also with linear model with recursive estimation of the parameters, the AMA, the recursive AMA, and this model is very special because it don't need a training database. So recursive, he estimates the parameters of the model recursively. So you don't need a training database, which is very interesting. But usually 1 year or 2 years to train the machine learning techniques.
And this is Skip. I would add that the length of time for what we've seen is in some ways secondary to the quality of the data set used for training. So whether it's a PV power output from a meter on a PV system, importance of that data actually reflecting the PV operation, irradiance data as well used in training models. If of poor quality, we like to use maybe somewhat overused term in software, but those training models can be very much a garbage in, garbage out type of model. So if you feed it bad training, it's going to have a hard time actually learning from and the model improving from what the real conditions are and what will really impact and improve the forecast prediction.
Okay, thank you all. Next question. Can the implementation of multiple PV arrays distributed over a large geographical region such as 500 square kilometers dramatically improve the aggregate or average solar power forecast accuracy? And then along these same lines, have electric power utilities actively supported intelligent distribution of PV arrays within a geographic region? So Skip, I'll start with you and then I'll go to Elke because the question actually came in during Elke's talk, but I think Skip, you may have addressed that as well. And then Philippe, if you have anything to add at the end, that's fine.
Okay, thanks, Dave. Yes, that's so. I think what I was hoping to show in one of my slides with the hit-miss metric specifically is that when you take the prediction across a larger area, the accuracy, at least from a utility standpoint of reliability, seems to indicate, now for that region that we were trialing, seems to indicate that there is a tighter prediction and more accurate capability across a larger area. For the second part of the question, I think it's difficult to broadly generalize across all of the utilities that we work with. I think the best thing I can add regarding utility steps in promoting that type of of installment of PV is that the ones that we work with and talk to are very much aware of the growth of PV, and they see the value of what it can provide as well and the tools that can be applied to help increase that value. So I think it goes to one of my last conclusion points in that this type of integration technology is needed to help support integration of PV.
Okay, Elke, did you have anything to add? Or Philippe?
No, yeah, I would say also, I mean, the accuracy of aggregates of PV over large areas, there is a much higher accuracy because of this spatial balancing effect. It's much more difficult to predict the specific one cloud over one specific PV power plant than generally predicting cloudy or clear conditions. And yeah, from the side of the grid, to benefit from this balancing effect, the grid has to be strong enough that the PV power from the different locations can be transported from one location to the other. So this balancing effect can only be fully used if the grid is strong enough to transport the power from one place to the other.
Okay,
Yeah.
Thank you. Philippe, did you want to add anything?
No, nothing, Dave.
Okay, well, thank you. So the next question is from a colleague in Scotland, Edinburgh, Scotland. I noticed that our panelists use medium-range numerical weather prediction models. However, they seem to have a special interest in intraday forecasting, and so therefore, why not take local numerical weather prediction model providers who are where they are optimized for short-term local forecasts? Hope I was clear on that question. And Philippe, would you like to start with answering that?
If I well understand, the question is about, can we use some sort of mesoscale model instead of a global model like ECMWF to improve?
Yeah, I think that's what they're asking. Yes.
I think, yeah. Actually, we tested the WRF model for Laren Island, and we get worse results than the result we get with the ECMWF. To improve the result we got with WRF, we need to design a post-processing technique. But the original WRF forecasts were very bad compared to ECMWF. And ECMWF did quite well in La Réunion, and also when I speak with other colleagues, also in other parts of the world. So we try a local numerical weather prediction model like WRF with a mesoscale model, but for application, it was no good.
Elke, did you have anything to add to that?
Yeah, we don't use only the global model, but we also use the regional model, from Cosmo EU, from German Weather Service, and I think also SCIP, they also use different regional forecast models. And so we combine the different numerical weather prediction model to get optimized results. But evaluations of different regional models compared to global model ECMWF forecast didn't show better results than the global model forecast, even for intraday. For some regions and location, there is some improvement, but there is not a big difference or a big improvement with the regional models over the global model for solar irradiance forecasting for a lot of different models that have been tested. Okay,
and,
finished?
If I can add to that point, I did mention briefly the evaluation of WRF on a larger scale, but we have as well looked at the downscaled or mesoscale regions, and specifically at certain cloud types in time horizons that are not well served by the cloud motion vector. So we could call out the coastal fog formation in the state of California, and that variability is not caused by cloud advection, rather burn off or formation, and so we've evaluated specifically those regional models to address specific inefficiencies.
Okay, well, we're getting near the end. I would like to just maybe take one more question. I think some of the questions I see, they're getting answered already by the panelists, and that's good. I believe the plan is to have the panelists provide written answers to all of the questions and have them posted on the website. Maybe Joanna can, in her closing remarks, can give a little bit more detail about that. But before then, let's just take one more question. Did any of the panelists also apply their forecast models to the direct normal irradiance component? Who would like to start with that one? Philippe, let's start with you.
Not yet, but we plan, not yet for the moment. But I presume that forecasting the DNI will be more difficult than GHI. So, but for the moment, not yet.
Skip, do you have anything to add there?
Yeah, I know we
DNI forecasting.
Yep, we generate DNI forecast as part of the input into tilted plane irradiance computation. So our GHI forecast and DNI forecasts are generated separately. Our focus similarly has been, because of GHI being a primary driver for PV, but we are starting to look with historical data at the uncertainty in that direct component as it relates to the ability to accurately transpose to plane of array. And I think there's a lot of good research topics that I've seen recently on that area, and not only relying on uncertainty for the GHI, but looking at how the direct component can contribute to uncertainty in the tilted plane.
Okay, thanks, Skip. And Elke, did you have anything you wanted to add there on the DNI forecasting?
No, not too much. I mean, we haven't looked very detailed in that. We're doing the same as Skip. We're doing it as a part of the tilt conversion process, and we have done some preliminary evaluations, but nothing really to present.
Okay, well, thank you. I think there are some institutions around the world that may be looking at DNI forecasting, and perhaps into some future webinar we can put together some talks on that topic as well. But at this point, I'd just like to express my thanks to all of the panelists for their excellent presentations and the response to the questions. I think I would now like to turn this back over to Joanna to close out the webinar. Maybe she can give us some last-minute information about how you may get access to the webinar and to the answers in the next few days and weeks.
Yes, thank you, Dave. Thank you also from me to all the panelists who shared their time and their knowledge with us in this ISIS webinar. And Dave, thank you to you for moderating. And of course, thank you to our audience for joining from all over the world. We had people from Mexico, Spain, USA, Germany, Canada, South Africa, Reunion Island. So a lot of people joined today for the webinar. Thank you all for coming and for your interesting questions. The unanswered questions, we'll try to get some questions to them and post them in the ISIS members area. So in this members area, you just log into your ISIS account if you have an active membership, and you'll see all the webinar recordings, the presentations, and the answers to the questions. If you are not an ISIS member, take a look at the website join.isis.org and have a look at our membership services and benefits, and you can sign up online quickly and easily. Okay, that's all we have time for today, I'm afraid. Next month we will have another ISIS webinar. They're every month. So do look out for the next webinar on our website. Please interact with us on social media. We have Facebook, Twitter, LinkedIn, YouTube and Google, and please complete the survey at the end of the webinar to give us some information about how to improve these services. Okay, have a nice day, evening, morning, whatever time it is in your part of the world, and see you in the next